everyone, here's a video on inverses of functions. The additive inverse of 3 is -3. The multiplicative inverse of 5 is 1/5. The multiplicative inverse of the matrix A is the inverse of A. You can also find and apply inverses to relations and functions. The inverse of a relation consisting of all ordered pairs x and y is the set of all ordered pairs y, x. So let's start out by graphing these ordered pairs and connecting them. There it is. Now let's switch the x and the y values in each ordered pair and graph the new ordered pairs. So what we're going to do is plot the points 2, 0, 4, 1, 5, 2, 6, 4, and 7, 8. And there's our other one. So now let's draw the line y equals x, as seen here in orange. So what do we notice about the two graphs? Well, they are a reflection of each other over the line y equals x. So by switching the x and y values, we reflected these ordered pairs over the line y equals x. Since the graph of an inverse relation is the reflection of the graph of the relation across the line y equals x, you can graph the inverse of a function by reflecting the function over the line y equals x, or by switching the x and y values of the original function and graphing the new ordered pairs. The inverse of a function is noted by f to the power of -1 x. So we just add in that little -1. So let's graph f of x equals x squared and f of the inverse of f of x, and then we'll list the domain and range of each. So here's f of x equals x squared, and in purple you see the inverse of f of x. So the domain of f of x, our regular x squared, is all real numbers, and the range is the y values greater than or equal to 0. And the domain of the inverse of f of x is the x values greater than or equal to 0, and the range is all real numbers. So what do we notice about the domain and range for f of x and f inverse of x? Well, they're switched. Is the inverse of f of x a function? So looking at this purple function, purple graph, is that a function? Actually, it's not, because it fails the vertical line test. Could we decide if the inverse of a function is also a function without graphing the inverse? Yes, we can. We can use a horizontal line test on the original function, f of x, and if it passes it, then it has an inverse function. If it fails it, then the inverse is not a function. Okay, so let's look at another example. Let's graph f of x equals x plus 2 and its inverse. So in red, I'll graph f of x, which is x plus 2, so the y intercept is 2, the slope is 1, so we'll go up 1 over 1, and so on. And then in purple, I'll graph the inverse. So that means we're supposed to take each ordered pair and reflect it across the line y equals x, or in other words, just switch the x and the y values. So this point was at 0, 2, so let's graph the point 2, 0. This was the point 1, 3, so let's graph the point 3, 1. This is the point 2, 1, 2, 3, 4, so we'll graph 1, 2, 3, 4, 2. So at this point you can see what the line looks like. And it doesn't look like it changed all that much, but notice that it's still reflected across the line y equals x. So the domain for f of x is all real numbers, and the range is also all real numbers. Here, the domain for the inverse function is all real numbers, and so is the range. So what is the equation for the inverse of f of x? So f inverse of x, looking at our graph, our y-intercept is -2, and our slope is +1, so we'll have x minus 2. So how could we get the equation without graphing the inverse? Well, since we switched the x and y values of our graphs, of the ordered pairs to graph them, we can switch the x and y in the function. So if we started out with y equals x plus 2, that was our original function, then what we can do is switch the x and the y, so we'll have x equals y plus 2, and then solve for y, so we have another function equal to y, so I'll have x minus 2 equals y. So that tells us that the inverse function is y equals x minus 2. So for each of these examples, let's find out the inverse function or the inverse equation for each of these functions. So we're going to do the same thing we did before and just switch the x and the y. So if this was y equals 3x, then we're going to switch it into x equals 3y, and then we'll solve for y again. So on this one, we'll get y equals x over 3, or 1/3 x. So our inverse function is 1/3 x. On the next one, same thing. So we have y equals 2/3 x plus 6. Then we'll switch the x and the y, so we'll have x equals 2/3 y plus 6, and solve. So we'll subtract the 6. And then to get rid of the 2/3 here, we can multiply both sides by 3/2. So here we'll have y equals, distribute the 3/2, we'll have 3/2 x, and the -6 times 3 is -18 divided by 2 is -9. So the inverse function of x is 3/2 x minus 9. On x squared, let's find the inverse. So if y is x squared, then switch it so that it's x equals y squared. To get y by itself, we'll square root both sides. So we get y equals the square root of x. So the inverse function is y equals, the inverse function is the square root of x. And that should make sense because x squared and the square root, they're inverses of each other. So let's graph g of x equals x plus 2 and the inverse. So in red, I've got our parabola moved up 2, and then in purple, I've got our inverse function, which you can get by switching the x and the y and solving for y again. So the equation for the inverse of g is g inverse, should have drawn that in purple, oh well, x minus 2. So I want you to try solving that one by switching the x and the y. The domain for g of x is all real numbers. The range is y values greater than or equal to 2. But for the inverse, it's the x values greater than or equal to 2. And the range here is actually the y values greater than or equal to 0, so that way it stays a function. So in this last part, if f of x is equal to x squared as a parent function, describe the relationship between f of x and g of x. Well, they're reflected over the line y equals x, but they have not completely identical graphs because g of x has to remain a function. Because if we include the bottom part, it would fail the vertical line test. If h of x is positive and negative square root of x, which means not only the top part would be there, but the bottom part would be there as well, Describe the relationship between h of x and g inverse of x, back here, that purple function. Well, the inverse of g of x is actually just the top part, whereas h of x is the entire thing. And so what can be said in terms of transformations about a function and its inverse? Well, as seen as our graph, up on the original meant right on the inverse, and so the opposite would be true. Down would mean left on the inverse. They're the same distance from the line y equals x, but sometimes it doesn't include the whole thing because we have to make sure that it stays a function. So the purple part, for example, up here, we only included the top part of the sideways parabola because the bottom part would make it fail. I hope that made sense, and I'm sorry if I kind of rushed there at the end, but I'll see you later and have a great day.